Lecture 54 notes, hypothesis testing for population proportions examples. All right, so first example. At What's It Gadgets, Inc., management boasts a defect rate of no more than 1% on their Monday morning computer motherboard assembly line. Monday morning is sometimes a time when there are more defects. So they're boasting a defect rate of no more than 1%. You are hired to see if their boast is worthy of belief. So, if P is the actual Monday morning defect rate on the assembly line, then our null and alternative hypotheses are H naught is that the actual rate is, it says that they boast that it's no more than 1%. So really, we could say it's 0.1, but really they're saying less than or equal to 0.01, sorry, 1/100th, right? Okay, notice that I have a case here where the null hypothesis contains inequality. That's all right, it also contains equality too, right? They'd like to say, hey, it's no more than 1%. If it's less than 1%, that's great, right? But the alternative hypothesis then that we're really testing this against would be, is it greater than 1? So it's a right-tailed test, okay? All right, you're going to collect a simple random sample of size n motherboards, keeping track of how many are defective. That is, getting a defective motherboard be a success, you will perform n independent trials. You'll grab one randomly, test it. Is it defective or not? Each with a probability of success assumed to be under the null hypothesis of 0.01. All right, and we'll keep track of the number of successes. How big must n be? Well, we got to have n p naught be bigger than or equal to 5 and n q naught be bigger than or equal to 5. Well, if p naught, this is our p naught, right? This is what we're assuming under the null hypothesis is 0.01. I need n times 0.01 to be bigger than or equal to 5. If you divide through, you get that n must be bigger than or equal to 500. And what about down here? Well, what's q naught? Q naught is 1 minus 0.01, right? 1 minus P naught. 1 minus P naught is 1 minus 0.01, so it's 0.99. So I need n times 0.99 to be bigger than or equal to 5. And that just says that n has to be, well, if it's 5, it won't quite do it, so it has to be bigger than or equal to 6. So clearly, if I have n bigger than or equal to 500, I've got a big enough sample. So that's a pretty big sample. It's not, not 30 like before, all right? And that has to do with the fact that we're looking or examining a proportion or a probability of success that's pretty small. It's 1/100th. So we got to get a big sample to make sure we get enough in there to test that properly. And I just say here, we'll use n equal 1,000, all right? So we're going to do 1,000 trials. That's bigger than 500, so we're good to go. So in testing our 1,000 motherboards, we find that x equals 17 of them are defective. How many defectives could we have? What could that x value be? We could have no defectives, that's 0, all the way up to 1, 2, 3, 4, 5, up to all 1,000, right? So it could be any value between 0 and n, right? And here it's 17, right? So p hat is x over n, which is 17 over 1,000, so it's 0.017, right? Okay, let's compute the test statistic. The test statistic is, remember, it's normal 0, 1, so it's a z random variable. It's p hat minus p naught over the square root of p naught times q naught over n. That's equal to p hat is 0.017 minus p naught is 0.01, all divided by the square root of p naught, 0.01, times q naught, 0.99, all divided by n, which is 1,000. And if you work that all out, you get 2.22474, etc., right? Okay, well now I'm going to go into my z-table. And so I'll use z-score equal to 2.22, since the table I'm using goes out to only out to the hundredths, right, for the z-score. That's good enough. And what do I get? I'll draw the little picture here. I get Out here, I get, at 2.22, I get all the area to the left is what? It's 0.9868. So, excuse me, the tail probability associated with this, which is the p-value, is 1 minus 0.9868, so it's 0.0132, right? Okay. And what do I say? I say, looks to me like we probably should reject with a p-value that small. It's, you know, a little more than 1%. If we were, again, if we had preset our significance level at 1%, we would not reject. We would fail to reject the null. But we didn't preset it, and I'm going to say that's a pretty small p-value. I'm going to reject. So I say here, what's my conclusion? Our conclusion. With a p-value, it's nice that we're with a z-random variable. We can compute that p-value exactly, right, by just looking at a table, right, just that tail probability. With a p-value of about about 0.0132, we have sufficient. Why we find sufficient evidence. Reason to reject the defect. Sufficient reason to reject that the defect rate is no more than 1%. Sadly, it appears to be greater, more, higher than 1%. Right, that is what we have shown. Okay, next example. Tossing the coin. So read that while I rub this out. We're going to try to figure out whether a coin is fair. And I say, let's toss this coin a bunch of times and try to decide from that if the coin is fair. That requires you to interpret what that all means, right? You have to come up with an understanding and frame it in terms of what we've been doing here, right, of what it means to say that a coin is fair. So what do I say? I say, you were told to pull a coin out of your pocket and test to see if it is fair. To do this, let's agree that getting a heads when we toss the coin will be considered a success. Certainly there are only two outcomes, right? Heads or tails. We don't think the coin's going to land on its edge, right? It's either head or tail. Then if P is the probability of a success each time we toss the coin, our hypotheses are H naught fair would mean that P is 1/2 or 0.5, right? And not fair would simply mean that the probability is not 1/2. Maybe bigger, maybe smaller, we don't know. So this is a two-tailed test, okay? All right, we're going to have n independent tosses. Oh, I mean, there's something parenthetical I want to say here. P is the probability, right, of getting a head or a tail. That's how we're kind of thinking of it right now. But you can also think of it as the proportion of heads we would obtain if we were to toss the coin indefinitely. We toss it 10 zillion times, and we expect half of them to come up heads because the probability each time is heads. So again, we have a connection between probability and proportions. Really, we're looking at population proportions here, but we can interpret this probability as a population proportion, so we can do a hypothesis test on it. Okay, we're going to have n independent tosses, n independent trials, with the probability of success under the null hypothesis being 0.5, 1/2. N must be at least, well, you know, look, n times p naught, there's p naught, 1/2. That's n times 0.5, and that's got to be bigger than or equal to 5. And n times q naught, Well, Q naught, of course, is 1 minus P naught, which is 1 minus a half, which is also a half. Fair coin. Probability is heads is a half, probability tails is a half as well. So NQ naught is going to be also n times 0.5, and that's got to be greater than or equal to 5. Clearly, if I divide through, these both say that n has to be bigger than or equal to 10. Right? So actually pretty small this time. The sample size we need is pretty small, but I just say we're going to do 100 tosses. We'll let n be 100. So we toss the coin 100 times, and we get 43 heads in our 100 tosses. Okay, that's not real close to 50. Is it enough off of 50 that maybe we think, oh, it looks like, because we expect 50, right? We expect half of them to be heads, because proportion should be a half, right? So that kind of maybe suggests it's not a fair coin. Let's see. What's p hat? P hat is x over n, where x is the number of successes, the number of heads, and n is the number of coin tosses. So we get 0.43, right? Not 0.5. What's the test statistic? Test statistic is p hat minus p naught divided by the square root of p naught times q naught divided by n. That is, p hat is 0.43 minus p naught is 0.5, right? 1/2, so 0.5 divided by the square root of p naught, which is 0.5, times what's q naught? Q naught is a half, which is also 0.5, divided by n, the number of times I tossed the coin. And you work that out, and you get negative 1.4. Okay, and that's a z-score, right? That's a z-score again. Okay, so what's the p-value? Well, if you go look, here's negative 1.4. What you get is, you look it up and you get 0.808, I think. Is that what I get? Or is it? Yeah, 0.0808, sorry, 0.0808. Okay, but this is a two-tailed test, right? And if you remember that the p-value is everything outside of that distance away from the origin. So I have to come over here and I have to do the symmetric thing. I have to fold over and I get this tail as well. So the p-value is 2 times 0.0808 because it's a two-tailed test. So we get 0.1616. That's a little over 16%. That's kind of a big p-value. And again, if we had had a significance level as high as 10%, which is a really, really high significance level, we would fail to reject the null, right? We would fail to reject the null hypothesis, even with a high significance level, because the tail probabilities associated with our test statistic are so high. So our conclusion, I think, should be, with such a high p-value, conclusion, such a high p-value, it's greater than 16%. You don't usually give p-values as percentages, but greater than 0.16, right? We fail to reject. Fail to reject that the probability of heads is 1/2, all right? We have insufficient evidence to conclude the coin is not fair. All right. It may be not fair, right? That's You know, that's kind of low, 43 out of 100, but it's not so low, again, that it is a really, really unusual value, and that's what we're saying, right? Its tail probabilities associated with it are big enough that we feel reasonably that it could have just happened by chance, even if the coin were fair. So we don't have good enough reason to say that it's not fair. I got one more example, and that is from the world of politics. So go ahead and start reading that, and I'll get this rubbed out so we can get to it. And it's in the world of politics where population proportions, testing for population proportions, you see it a lot. All right, and that should make sense if you give some thought to this example. You can see that it just makes sense that that's the kind of thing that we would use hypothesis tests for proportions for a lot on. Okay. Senator I Am Corrupt is considering running for president. He's decided that he will make a run for it if, only if at least 30% of the voters in the nation, I lost my place, okay, have a favorable opinion of him initially, all right? Does he at least have 30% support just starting out? He's hired your polling agency to determine if he should run. What are the null and alternative hypotheses? The null hypothesis is that the proportion, he wants it to be at least 30%, right? So I would say it's really greater than or equal to 0.3, right? That's the null hypothesis. The alternative hypothesis, then, bad for corrupt is if p is less than 0.3. Okay, so you survey 400 randomly chosen voters and find that 60 of them have a favorable opinion of corrupt. Check your criteria to see if you can proceed. Okay, well, n equal 400, and they're independent trials. If I survey totally randomly 400 voters and ask them whether or not they support corrupt or have a favorable opinion of him, then it's either a yes or no question. So I have two categories, and they're totally independent, each one from the other. And what is NP? What is NP? Sorry, NP naught is 400 times 0.3, that's 120, that's bigger than or equal to 5. Well, what's NQ naught? Well, that's 400 times 1 minus 0.3, right? There's where Q naught is right there. So that's 400 times 0.7, that's Q naught, and that's 280. And that's bigger than or equal to 5. So we can certainly proceed, all right? We just need to have them both bigger than or equal to 5. Test statistic. I'm just going to leave it to you to calculate it. You should be able to put everything in and compute it, and you should get about negative 21. So stop me and see if you can run through and get negative 21. You just set it all up, p hat minus p naught over square root of p naught, q naught divided by n, and you should get that. The p-value here is less than 0.0001, right? The test statistic, this is a z random variable, right? Way the heck out on the tail. Okay, so what do you see from that? You see that at the, I did say up here somewhere, I didn't mention it. I say here, yeah, right here, using a 5% significant level, which is typical in political polling. 5% significant, what's your conclusion? Should corrupt run? Well, it's way the heck out and way beyond a 5% tail probability. Its tail probability is less than 0.0001. So at the 5% significance level, there is sufficient evidence to reject the claim that corrupt support is at least 30%. He should not run. I'm going to say that one more time. I'm not going to write it. At the 5% significance level, there is sufficient evidence to reject the claim that corrupt support is at least 30%. So we reject H naught very handily. He should not run is what we would tell him, right? Okay, so be sure you do the calculations here. I have space for you to do them. Be sure you do it and get that, and be sure you write the conclusion. We'll stop with those examples.